Chapter 1, Part 2 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Part 1, Chapter 1, Foundation of Sidereal Astronomy, Part 2. We have now to speak of Herschel's pioneering work in the skies, to explore with line and plummet the shining zone of the Milky Way, to delineate its form, measure its dimensions, and search out the intricacies of its construction was the primary task of his life, which he never lost sight of, and to which all his other investigations were subordinate. He was absolutely alone in this bold endeavor. Unaided, he had to devise methods, accumulate materials, and sift out results. Yet it may safely be asserted that all the knowledge we possess on this sublime subject was prepared, and the greater part of it anticipated, by him. The ingenious method of star gauging, and its issue in the delineation of the sidereal system as an irregular stratum of evenly scattered suns, is the best known part of his work. But it was in truth only a first rude approximation, the principle of which maintained its credit in the literature of astronomy a full half-century after its abandonment by its author. This principle was the general equality of star distribution. If equal portions of space really held equal numbers of stars, it is obvious that the number of stars visible in any particular direction would be strictly proportional to the range of the system in that direction, apparent accumulation being produced by real extent. The process of gauging the heavens, accordingly, consisted in counting the stars in successive telescopic fields, and calculating thence the depths of space necessary to contain them. The result of 3,400 such operations was the plan of the galaxy familiar to every reader of an astronomical textbook. Widely varying evidence was, as might have been expected, derived from an examination of different portions of the sky. Some fields of view were almost blank, while others, in or near the Milky Way, blazed with the radiance of many hundred stars compressed into an area about one-fourth that of the full moon. In the most crowded parts, 116,000 were stated to have been passed in review within a quarter of an hour. Here the length of his sounding line was estimated by Herschel at about 497 times the distance of Sirius, in other words, the bounding orb or farthest sun of the system in that direction, so far as could be seen with the 20-foot reflector, was thus inconceivably remote. But since the distance of Sirius, no less than of every other fixed star, was as yet an unknown quantity, the dimensions inferred for the galaxy were of course purely relative. A knowledge of its form and structure might, admitting the truth of the fundamental hypothesis, be obtained, but its real or absolute size remained altogether undetermined. Even as early as 1785, however, Herschel perceived traces of a tendency which completely invalidated the supposition of any approach to an average uniformity of distribution. This was the action of what he called a clustering power in the Milky Way. Many gathering clusters were already discernible to him even while he endeavored to obtain a true mean result, on the assumption that each star in space was separated from its neighbors as widely as the sun from Sirius. It appears, he wrote in 1789, that the heavens consist of regions where suns are gathered into separate systems, and in certain assemblages he was able to trace a course or tide of stars setting towards a centre, denoting not doubtfully the presence of attractive forces. 13 years later he described our sun and his constellated companions, as surrounded by a magnificent collection of innumerable stars called the Milky Way, which must occasion a very powerful balance of opposite attractions to hold the intermediate stars at rest. For though our sun and all the stars we see may truly be said to be in the plane of the Milky Way, yet I am now convinced, by a long inspection and continued examination of it, that the Milky Way itself consists of stars very differently scattered from those which are immediately about us. This immense aggregation, he added, is by no means uniform. Its component stars show evident signs of clustering together into many separate allotments. The following sentences, written in 1811, contain a definite retraction of the view frequently attributed to him. "I must freely confess," he says, "that by continuing my sweeps of the heavens, my opinion of the arrangement of the stars and their magnitudes, and of some other particulars, has undergone a gradual change; and indeed, when the novelty of the subject is considered, we cannot be surprised that many things formerly taken for granted should on examination prove to be different from what they were generally, but incautiously, supposed to be. For instance, an equal scattering of the stars may be admitted in certain calculations, but when we examine the Milky Way, or the closely compressed clusters of stars of which my catalogues have recorded so many instances, this supposed equality of scattering must be given up." Another assumption, the fallacy of which he had not the means of detecting since become available, was retained by him to the end of his life. It was that the brightness of a star afforded an approximate measure of its distance. Upon this principle he founded in 1817 his method of limiting apertures, by which two stars brought into view in two precisely similar telescopes were equalized by covering a certain portion of the object glass collecting the more brilliant rays. The distances of the orbs compared were then taken to be in the ratio of the reduced to the original apertures of the instruments with which they were examined. If indeed the absolute lustre of each were the same, the result might be accepted with confidence; but since we have no warrant for assuming a standard star to facilitate our computations, but much reason to suppose an indefinite range, not only of size but of intrinsic brilliancy, in the suns of our firmament, conclusions drawn from such a comparison are entirely worthless. In another branch of sidereal science, besides that of stellar aggregation, Herschel may justly be styled a pioneer. He was the first to bestow serious study on the enigmatical objects known as nebulae. The history of the acquaintance of our race with them is comparatively short. The only one recognized before the invention of the telescope was that in the girdle of Andromeda, certainly familiar in the middle of the 10th century to the Persian astronomer Abdurrahman al-Sufi, and marked with dots on Spanish and Dutch constellation charts of the 14th and 15th centuries. Yet so little was it noticed that it might practically be said, as far as Europe is concerned, to have been discovered in 1612 by Simon Marius, mayor of Genzenhausen, who aptly described its appearance as that of a candle shining through horn. The first mention of the great Orion nebula is by a Swiss Jesuit named Cysatus, who succeeded Father Scheiner in the chair of mathematics at Ingolstadt. He used it, apparently without any suspicion of its novelty, as a term of comparison for the comet of December 1618. A novelty, nevertheless, to astronomers it still remained in 1656, when Huygens discerned, as it were, an hiatus in the sky, affording a glimpse of a more luminous region beyond. Halley, in 1716, knew of 6 nebulae, which he believed to be composed of a lucid medium diffused through the ether of space. He appears, however, to have been unacquainted with some previously noticed by Hevelius. Lacaille brought back with him from the Cape a list of 42, the first fruits of observation in southern skies, arranged in 3 numerically equal classes; and Messier, nicknamed by Louis XV. The ferret of comets, finding such objects a source of extreme perplexity in the pursuit of his chosen game, attempted to eliminate by methodizing them, and drew up a catalogue comprising in 1781 103 entries. These preliminary attempts shrank into insignificance when Herschel began to sweep the heavens with his giant telescopes. In 1786 he presented to the Royal Society a descriptive catalogue of 1,000 nebulae and clusters, followed 3 years later by a second of as many more, to which he added in 1802 a further gleaning of 500. On the subject of their nature his views underwent a remarkable change. Finding that his potent instruments resolved into stars many nebulous patches, in which no signs of such a structure had previously been discernible, he naturally concluded that resolvability was merely a question of distance and telescopic power. He was, as he said himself, led on by almost imperceptible degrees from evident clusters, such as the Pleiades, to spots without a trace of stellar formation, the gradations being so well connected as to leave no doubt that all these phenomena were equally stellar. The singular variety of their appearance was thus described by him: "I have seen," he says, "double and treble nebulae variously arranged, large ones with small seeming attendants, narrow but much extended lucid nebulae or bright dashes, some of the shape of a fan resembling an electric brush issuing from a lucid point, others of the cometic shape with a seeming nucleus in the centre, or like cloudy stars surrounded with a nebulous atmosphere. A different sort again contain a nebulosity of the milky kind, like that wonderful inexplicable phenomenon about Theta Orionis, while others shine with a fainter mottled kind of light, which denotes their being resolvable into stars." These curious objects he considered to be no less than whole sidereal systems, some of which might well outvie our Milky Way in grandeur. He admitted, however, a wide diversity in condition as well as compass. The system to which our sun belongs he described as a very extensive branching congeries of many millions of stars, which probably owes its origin to many remarkably large as well as pretty closely scattered small stars that may have drawn together the rest. But the continued action of this same clustering power would, he supposed, eventually lead to the breaking up of the original majestic galaxy into 200 or 300 separate groups, already visibly gathering. Such minor nebulae, due to the decay of other branching nebulae similar to our own, he recognized by the score, lying, as it were, stratified in certain quarters of the sky. One of these nebulous beds, he informs us, is so rich that in passing through a section of it, in the time of only 36 minutes, I detected no less than 31 nebulae, all distinctly visible upon a fine blue sky. The stratum of Coma Berenices he judged to be the nearest to our system of such layers, nor did the marked aggregation of nebulae towards both poles of the circle of the Milky Way escape his notice. By a continuation of the same process of reasoning, he was enabled, as he thought, to trace the life history of nebulae from a primitive loose and extended formation, through clusters of gradually increasing compression, down to the kind named by him planetary, because of the defined and uniform discs which they present. These he regarded as very aged and drawing on towards a period of change or dissolution. This method of viewing the heavens, he concluded, seems to throw them into a new kind of light. They now are seen to resemble a luxuriant garden, which contains the greatest variety of productions in different flourishing beds. And one advantage we may at least reap from it is, that we can, as it were, extend the range of our experience to an immense duration. For, to continue the simile which I have borrowed from the vegetable kingdom, is it not almost the same thing whether we live successively to witness the germination, blooming, foliage, fecundity, fading, withering, and corruption of a plant, or whether a vast number of specimens, selected from every stage through which the plant passes in the course of its existence, be brought at once to our view? But already this supposed continuity was broken. After mature deliberation on the phenomena presented by nebulous stars, Herschel was induced in 1791 to modify essentially his original opinion. "When I pursued these researches," he says, "I was in the situation of a natural philosopher who follows the various species of animals and insects from the height of their perfection down to the lowest ebb of life. When arriving at the vegetable kingdom, he can scarcely point out to us the precise boundary where the animal ceases and the plant begins, and may even go so far as to suspect them not to be essentially different. But recollecting himself, he compares, for instance, one of the human species to a tree, and all doubt upon the subject vanishes before him. In the same manner we pass through gentle steps from a coarse cluster of stars, such as the Pleiades, till we find ourselves brought to an object such as the nebula in Orion, where we are still inclined to remain in the once adopted idea of stars exceedingly remote and inconceivably crowded as being the occasion of that remarkable appearance. It seems, therefore, to require a more dissimilar object to set us right again. A glance like that of the naturalist, who casts his eye from the perfect animal to the perfect vegetable, is wanting to remove the veil from the mind of the astronomer. The object I have mentioned above is the phenomenon that was wanting for this purpose. View, for instance, the 19th cluster of my 6th class, and afterwards cast your eye on this cloudy star, and the result will be no less decisive than that of the naturalist we have alluded to. Our judgment, I may venture to say, will be, that the nebulosity about the star is not of a starry nature." The conviction thus arrived at of the existence in space of a widely diffused shining fluid, a conviction long afterwards fully justified by the spectroscope, led him into a field of endless speculation. What was its nature? Should it be compared to the coruscation of the electric fluid in the aurora borealis, or to the more magnificent cone of the zodiacal light? Above all, what was its function in the cosmos? And on this point he already gave a hint of the direction in which his mind was moving by the remark that this self-luminous matter seemed more fit to produce a star by its condensation than to depend on the star for its existence. This was not a novel idea. Tycho Brahe had tried to explain the blaze of the star of 1572 as due to a sudden concentration of nebulous material in the Milky Way, even pointing out the space left dark and void by the withdrawal of the luminous stuff. And Kepler, theorizing on a similar stellar apparition in 1604, followed nearly in the same track. But under Herschel's treatment, the nebular origin of stars first acquired the consistency of a formal theory. He meditated upon it long and earnestly, and in two elaborate treatises, published respectively in 1811 and 1814, he at length set forth the arguments in its favour. These rested entirely upon the principle of continuity. Between the successive classes of his assortment of developing objects, there was, as he said, perhaps not so much difference as would be in an annual description of the human figure were it given from the birth of a child till he comes to be a man in his prime. From diffused nebulosity, barely visible in the most powerful light-gathering instruments, but which he estimated to cover nearly 152 square degrees of the heavens to planetary nebulae supposed to be already centrally solid, instances were alleged of every stage and phase of condensation. The validity of his reasoning, however, was evidently impaired by his confessed inability to distinguish between the dim rays of remote clusters and the milky light of true gaseous nebulae. It may be said that such speculations are futile in themselves and necessarily barren of results, but they gratify an inherent tendency of the human mind, and, if pursued in a becoming spirit, should be neither reproved nor disdained. Herschel's theory still holds the field, the testimony of recent discoveries with regard to it having proved strongly confirmatory of its principle, although not of its details. Strangely enough, it seems to have been propounded in complete independence of Laplace's nebular hypothesis as to the origin of the solar system. Indeed, it dated, as we have seen, in its first inception from 1791, while the French geometrician's view was not advanced until 1796. We may now briefly sum up the chief results of Herschel's long years of watching the heavens. The apparent motions of the stars had been disentangled, one portion being clearly shown to be due to a translation towards a point in the constellation Hercules of the sun and his attendant planets, while a large balance of displacement was left to be accounted for by real movements, various in extent and direction, of the stars themselves. By the action of a central force, similar to, if not identical with, gravity, suns of every degree of size and splendour, and sometimes brilliantly contrasted in colour, were seen to be held together in systems, consisting of 2, 3, 4, even 6 members, whose revolutions exhibited a wide range of variety, both in period and in orbital form. A new department of physical astronomy was thus created, and rigid calculation for the first time made possible within the astral region. The vast problem of the arrangement and relations of the millions of stars forming the Milky Way was shown to be capable of experimental treatment and of at least partial solution, notwithstanding the variety and complexity seen to prevail, to an extent previously undreamt of, in the arrangement of that majestic system. The existence of a luminous fluid diffused through enormous tracts of space and intimately associated with stellar bodies was virtually demonstrated, and its place and use in creation attempted to be divined by a bold but plausible conjecture. Change on a stupendous scale was inferred or observed to be everywhere in progress. Periodical stars shone out and again decayed. Progressive ebbings or flowings of light were indicated as probable in many stars under no formal suspicion of variability. Forces were everywhere perceived to be at work, by which the very structure of the heavens themselves must be slowly but fundamentally modified. In all directions groups were seen to be formed or forming, tides and streams of suns to be setting towards powerful centres of attraction, new systems to be in process of formation, while effete ones hastened to decay or regeneration when the course appointed for them by infinite wisdom was run. And thus, to quote the words of the observer who had looked farther into space than ever human being did before him, the state into which the incessant action of the clustering power has brought the Milky Way at present is a kind of chronometer that may be used to measure the time of its past and future existence, and although we do not know the rate of going of this mysterious chronometer, it is nevertheless certain that, since the breaking up of the parts of the Milky Way affords a proof that it cannot last for ever, it equally bears witness that its past duration cannot be admitted to be infinite. End of Part 1. Chapter 1, Part 2.